In today's lesson, we're going to look at reaction profiles. So we're going to move on from our basic definition of endothermic and exothermic. Before we do that, I just want you to do these first two task questions, just as a recap. So first one, I want you to define the word exothermic and give one example. Then I want you to tell me how to answer this statement here, or how do we answer this question. Explain your reasoning behind it. It is, in which reaction, exothermic or endothermic, is energy made? And I want you to explain your answer. I'll repeat again. In which reaction, exothermic or endothermic, is energy made? And then I want you to explain your answer. Whatever your answer is, whether you choose exothermic or endothermic or something else, I would like you to explain your answer. And could you feedback your answers on Teams, please? So learning question A and B, I would like your answer back on Teams. So pause the video here once you've got the title down, and can you answer the two learning questions? So when we're looking at exothermic and endothermic reactions, we can graphically show what is going on. Now, before we start looking at these diagrams, there are a few opening points I want you to take a note of first. First of all, these diagrams show the relative amounts of energy contained in the reactants and the products. And the units we're going to use are the units that are going to be used to measure the energy, the changes in the relative amount of energy contained in the reactants and products is going to be kilojoules per mole. So this is the units of the energy that we're going to measure this in. So just be aware of this. So the diagrams that we're going to look at show the relative amounts of energy contained in the reactants and the products. So can you put the subheading exothermic reactions? And we're going to now, I'm going to go through step by step in terms of how we actually represent an exothermic reaction in terms of an energy profile diagram. So could you, underneath your subheading exothermic reactions, can you draw a quick sketch of a graph with the axes like this? Okay, and ensure that you've got your graph correctly with the arrowheads as well, showing which way it's going forward. Okay, now, once you've got your axes, you will need to label the axes. So on the x-axis, we have progress of reaction. And on the y-axis, we're going to have energy. Now we're going to represent the reactants and the products for an exothermic reaction. So this is important when we look at the reactants and products in relation to each other. For exothermic reactions, they always take this particular pattern. So we'll take a line here, and we'll take a line here. Now we say that for exothermic reactions, the reactants are here and the products are lower in terms of energy as the reaction proceeds. So as the reaction proceeds, the reactants are at a higher energy level than the products for exothermic reactions. And we show this reaction as having taken place via this curved line like that. Now this tells us that the reaction is an exothermic reaction. Now let's draw that a bit better. So this is the typical way in which we express an exothermic reaction, with a curve going up, and we'll talk about this curve in a minute, but this is how we express exothermic reactions. Now, when we talk about an exothermic reaction, we're talking about energy being released to the surroundings, and this can be represented on this graph. You can find the energy released to the surroundings by looking at this. And what we do is we look at this portion here. This portion of the graph represents energy released to the surroundings. Okay, so energy released to the surroundings is represented here. So this quickly shows us via the energy profile diagram of an exothermic reaction. Now the products are at a lower energy level than the reactants. This means that when the reactants form the products, energy is transferred to the surroundings. And the difference between the energy levels of the reactants and the products is the energy change during the reaction, and that's measured in kilojoules per mole, as we looked at just moments ago, as we just talked about the units before. Now, an amount of energy equal to the difference in energy between the products and the reactants is transferred to the surroundings. And this is what makes it an exothermic reaction. And this is why the surroundings get hotter and the temperature rises. So you need to be aware of a typical exothermic reaction having this profile. Now, if we focus more on the curved part of the graph, so if we, looking at your diagram, we're going to focus now more on the curved part of the graph, and this refers to the activation energy. So I'm going to draw a separate diagram, but you can add it to your diagram that you already have. So on your axis, we have progression or progress of reaction. Now, because this is an exothermic reaction, what happens is that we have reactants and products, and the reactants being at a higher energy level. Remember, for an exothermic reaction, reactants are at a higher energy level than the products. So we have reactants and products. Now we're going to focus this graph onto the activation energy level. We're just going to look at the activation energy level in a bit more detail here. So because this is a reaction taking place and it's exothermic, I'm going to exaggerate the curve like this. Now, the activation energy level for this type of, for an exothermic reaction, we say can be found at this region. So the activation energy level is found at this region here. Let's move forward a bit there. Okay. It's at this region here. Now, notice the activation energy level is from this part here. So this is the activation energy level. So if we just label this is activation energy, and the energy needed or required to start the reaction. Okay, so this is the activation energy. Notice from the previous slide just a moment ago, we were looking at the energy released, and that is represented at a different point. Remember that the energy released from the reaction is here. Remember that the energy released from the reaction is represented here. Okay, so this is energy released. So do not get the two confused, where the activation energy level can be found and where the energy released to the surroundings can be found for an exothermic reaction. Now, what do we mean by activation energy? This is the minimum amount of energy needed for the colliding particles of the reactants to collide with the minimum amount of energy to cause a reaction. And this is known as the activation energy level. And unless that barrier is crossed, the reactants do not turn into products. So you cannot get the reaction progressing forward unless the activation energy level is reached. So can you take down this diagram? You can either add it to your diagram, but make sure you clearly identify where the activation energy level is in relation to the reactants and products. And could you put on your diagram that this is the energy required to start the reaction? And this is for an exothermic reaction. Now we're going to look at the endothermic reactions and how to represent them on energy profile diagrams. Now before we start, so I want you to put the subheading and get your axes drawn as well. And I want you to pause the video here, and I want you just to quickly on your piece of paper, I want you to label these axes first. So can you just pause the video here and can you label the axes first? Okay, so you should have the axes like this. Let's just put this down. You should have energy here on the y-axis and progress of reaction. It's the same for endothermic and exothermic. So progress of reaction is on the x-axis, energy is on the y-axis. Now, how do we represent this in terms of reactants and products, in terms of their relative energy differences? Okay. So as we previously looked at, we are going to represent the reactants first. Let's put this in red again. Okay, so we represent the reactants as being here. And then we say the products are here. So here are your reactants and here are your products for an endothermic reaction. Notice that in an endothermic reaction, the reactants are at a lower energy level than the products. So when we look at the relative difference in the energy of reactants and products in an endothermic reaction, the reactants are at a lower energy than the products. So if we were to say this reaction has proceeded forward and we draw a line to represent that, so this is our line saying that the reaction has proceeded forward. Now, the energy that is represented in terms of if it's giving out heat or taking in heat from the surroundings or taking in energy from the surroundings is represented here. And so the energy that is, because this is an endothermic reaction, energy is going to be taken in from the surroundings, and we represent that here. And let's just make it a bit clearer here. So if we say, there you are. So this arrow going from the reactants to the products, which is represented in yellow orange here, is showing the energy that is taken in from the surroundings. So this is why it is an exothermic reaction. So when we're trying to represent that energy taken in from the surroundings and the reactants take in that energy to make the products, we represent it via this line here. So we just say energy taken in. Taken in. Okay, so this is energy taken in from the surroundings, hence this is the endothermic reaction that's being represented. Notice again, I'll repeat again, the reactants are at a lower energy than the products. So essentially we say, you can look at it another way, you can also phrase it another way, you can say that here the products are at a higher energy level than the reactants. So as the reactants react to form products, energy is transferred from the surroundings to the reaction mixture. The temperature of the surroundings decrease as energy is taken in during the reaction. Therefore, the surroundings get colder. So if you were to measure this in terms of a practical experiment or investigation, and you were looking at an endothermic reaction, you would be looking for a decrease in temperature. Whereas if you are looking at an exothermic reaction, you would be looking at an increase in temperature. So can you just make a note of this energy profile diagram for an endothermic reaction? Make sure that you clearly identify how the energy is represented when it's taken in from the surroundings. And can you also make sure you clearly state on your diagram that the reactants are at a lower energy than the products. Now we're going to focus on the activation energy of an endothermic reaction. So we've looked at the overall energy. Now we're going to focus on the activation energy. So as before, make sure that our graph is correctly labeled. So this is progress of reaction on the x-axis. So progress of reaction is on the x-axis. Energy is on, make that a bit clearer. Energy is on the y-axis, and then we have to represent our reactants and products. So since it's an endothermic reaction, our reactants are going to be at a lower energy level than our products. So our products are going to be higher at a higher energy level because this is an endothermic reaction. So we say here are your reactants, and here are your products. Now, since we're looking at the activation energy, we're focusing more on that. We are looking at the curve part of the graph. So this is what we are essentially looking at. Now, the way to represent the activation energy level here if we extend the line from the reactance, just a dashed line here, it makes it easier to actually quickly identify the activation energy. Now, what you need to, let's put it in green as before. Now, the activation energy is the top part of the peak. It's exactly the same for an exothermic reaction in terms of where we're locating it. It's at the top part of the peak. So to represent it easily and bring it straight down to the level of the reactants, we locate the top part of the peak, and this is the same for exothermic reactions, and we bring it down to the reactants. Now, by extending the line on the reactants, it just makes it easier to identify the baseline of the reactants to the top part of the curve. And from the reactants to the top part of the curve, that is the activation energy level. So if we had to just label this, we'll say this is activation energy. So this is the activation energy. So can you, on your diagram, or we can draw it separately to the side because we're focusing only on the activation energy part of the graph. Can you add this to your diagram or draw a separate graph showing the activation energy and how we represent it for an endothermic reaction? Okay, now we're just going to put a few points down to summarize what we've looked at in both energy profile diagrams. So for exothermic reactions, a curved line drawn from the reactants to the products shows the course of the reaction. This is also true for endothermic reactions. Now, the difference in the energy between the reactants and the peak of the curve represents the amount of energy required for the reaction to take place. So these are our opening statements. I'll repeat again. A curved line drawn from the reactants to the products show the course of the reaction. The blue line was showing you the course of the reaction. The difference in energy between the reactants and the peak of the curve represents the amount of energy required for the reaction to take place. And I want you to tell me on Teams what this statement in yellow is referring to. So can you type back on Teams what this statement in yellow is referring to? So pause the video here, read this statement and take it down as well, where it says the difference in energy between the reactants and the peak of the curve represents the amount of energy required for the reaction to take place. What is this statement in yellow referring to? So just to sum up exothermic reactions, the products are at a lower energy level than the reactants. Energy is transferred to the surroundings when the reactants form into products. Because of this, the surrounding gets hotter and the temperature rises. So if the surrounding is getting hotter and the temperature is rising, this means in a practical investigation, if you are asked to investigate if a particular reaction, chemical reaction, was going to be exothermic or endothermic, you can look for a temperature rise. This will tell you that a chemical reaction is exothermic. So I'll repeat again, the products are at a lower energy level than the reactants. So referring back to your graph, you can see that for an exothermic reaction, the products are at a lower energy level. Energy is transferred to the surroundings when the reactants form into products. So when we get the formation of products in an exothermic reaction, energy is transferred to the surroundings. Therefore, the surroundings get hotter and there is a temperature rise. Can you take down these 3 points as a summary for exothermic reactions? So this briefly breaks down the energy profile diagram for exothermic reactions. Can you pause the video here and can you ensure that you have these 3 sentences in your notes? Now looking at the endothermic reaction. So let's just summarize what we have seen in terms of the energy profile diagram. So can you, while you are listening to me summarize it, can you have your diagram in front of you so you can take a look at it you can refer to it as we summarize it. Products are at a higher energy level than the reactants. Energy transferred from the surroundings to the reaction mixture. So energy is transferred from the surroundings to the reaction mixture, i.e. energy is transferred from the surroundings to the reactants. The temperature of the surroundings decrease. So as the reaction proceeds, because energy is transferred from the surroundings to the reactants, the temperature of the surrounding decreases. This is a fall in temperature. Now, the reason I've stated, you may think I'm stating the obvious, but if there is a fall in temperature, you need this piece of information to understand that this is what you will be measuring or looking for if you are doing this via an investigation. So if you're investigating an endothermic reaction, you would be looking for a fall in temperature. So quickly going through this again, in an endothermic reaction, products are at a higher energy level than the reactants. Energy is transferred from the surroundings to the reactants. The temperature of the surroundings decrease, and this is a fall in temperature. And the point of it being a fall in temperature is important because if you're investigating endothermic and exothermic reactions, if you have to talk about an experimental procedure, you are looking for a fall in temperature. Now we're going to summarize activation energy. This is the minimum amount of energy required for successful collisions between reacting particles to cause a reaction. So the minimum amount of energy required for successful collisions between reacting particles to cause a reaction. This is called the activation energy. Now, we represented the activation energy as the curve from the reactants to the top of the peak. That was the activation energy. So can you put down a subheading and can you take down this statement that sums up the activation energy? Now you can rephrase it in a different way if you want, but you must be clear that it is the minimum amount of energy required. You can also say it's the minimum amount of energy needed before colliding particles of reactants have sufficient energy to cause a reaction. And this energy needed to start the reaction is what is called the activation energy. So can you take down this statement or something similar to this by looking at your diagram, which helps you to understand what the activation energy is and how you would actually find it on a diagram, on an energy profile diagram, regardless of an endothermic or exothermic reaction. So far we have discussed what an exothermic reaction is, what an endothermic reaction is, and we've also mapped out these types of reactions on an energy profile diagram. Now we're going to talk about exothermic and endothermic reactions in terms of bonds breaking and bonds forming. So in a chemical reaction, there are 2 steps. Essentially, First step is chemical bonds between the atoms or ions are broken. The second step is new chemical bonds are formed to make the products. Now, step 1 and step 2 are not necessarily happening in that sequence. Sometimes they're happening simultaneously, because the two processes do not necessarily happen in sequence. All the bonds do not break, and then all the new bonds do not form. The bond breaking and making process happen at the same time. However, when we compare the energy required to break the bonds with the energy released when the new bonds are formed, it gives us the overall energy change. And this is what allows us to decide if an energy is exothermic or endothermic. But to make it easier for us to understand what is happening in terms of exothermic and endothermic, we need to understand that in a chemical reaction, chemical bonds between atoms or ions are broken and new chemical bonds are formed to make the products. Now let's see where exothermic and endothermic fit into these two steps. So looking at this whole concept of bond breaking and bond forming in terms of exothermic and endothermic reactions, let's see how we can put this down. So what we say is that energy has to be supplied to break chemical bonds. This energy is taken in from the surroundings. Therefore, breaking bonds is an endothermic process. I'll repeat that again. When we're breaking bonds, so when we're using energy to break chemical bonds, the energy must come from somewhere. It comes from the surroundings, and it's taken in to the chemical bonds and to break them. Therefore, breaking bonds is an endothermic process because energy is taken in from the surroundings. So can you take down those 3 bullet points that explain that bond breaking is an endothermic process? Now look at the sentences in yellow. Here it says, new bonds forming is due to energy released to the surroundings. Therefore, making bonds is, and I want you to tell me what that would be. So this statement in yellow simply says that new bonds forming is due to energy released to the surroundings. Therefore, making bonds is what? What would it be? I want you to write down the sentence in yellow and complete it in your answers. And also, I want you to send your answer to me on Teams as well. So once you've taken down the 3 bullet points at the top describing how breaking bonds is an endothermic process, I want you to look at the sentence in yellow. I want you to write it out in your notes and complete it with the correct answer. And I want you to also send me that answer on Teams. If we were to map this bond breaking and bond forming in terms of a reaction, we can take the reaction of hydrogen and oxygen reacting together to make water. So if we were to take hydrogen, H2 and H2 here, and we react that with an oxygen molecule, this gives us a water molecule and another water molecule. Sometimes it's easier to work this backwards if you want to see how much of the reactants you need. However, you can see here, it doesn't matter which way you look at the equation, you should still get the same still the same type of structural formula that you're seeing. But here you can see the H2 molecule, 2 H2 molecules and 1 O2 molecule reacting together to give 2 H2O molecules. Now, in terms of bond breaking and bond forming, the hydrogen bonds here needed to be broken. Let's make it a bit more easy. Okay, the hydrogen bonds needed to be broken, and also the oxygen bonds needed to be broken. The bonds between the oxygen molecule needed to be broken. So you can see the zigzag line. This represents the hydrogen, the bonds between the hydrogen molecules being broken, and also it represents the bonds being broken between the O2 molecule. And notice I'm saying bonds between the O2 molecule, not bonds inside the oxygen atom. These bonds are being broken when we're forming water between molecules. Hydrogen exists as H2 and oxygen exists as O2. And this forms two water molecules. So this is an example of bonds forming and bonds breaking if we had to represent it in this format. You can be asked to represent it in other types of chemical reactions. It requires you to know what the products and what the reactants are, and then you can make a representation like this. So this is showing hydrogen and oxygen reacting to make water. The bonds between the hydrogen atoms and between the oxygen atoms have to be broken so that bonds between the oxygen atoms and the hydrogen atoms in water can be formed. So can you take this example down? So your task right now for the next 18, I don't want to say 20 minutes, let's say 18 minutes, it should be enough time. A minute to mark should give you sufficient time to do this task. What I want you to do is to answer questions 1 to 3C. So all of question 1, 2 and 3 you should be able to answer. Now where it says, for example, for 3B, it says using a diagram like figure 5, this is the example for water. So this part here is your example for water. So looking at that example, okay, I want you to show the bonds being broken and new bonds being made in the reaction between methane, CH4, and oxygen. And the products are carbon dioxide and water. So that's just a note on 3B. So now can you pause the video? Can you make sure that you are answering these questions in full sentences, not one-word answers, in full sentences. Some of these answers are descriptive answers, and you need to make sure that you're describing what the reactions are showing you in terms of if it's exothermic or endothermic. So we'll say 18 minutes now, and can you make sure that you answer these questions on a separate document, and can you upload your answers to me? So once you've finished this task, can you upload your answers to me on Teams? For this task, you're going to have to do some research on your own. So we are going to be looking at how we can use energy transfer from the reactions, whether they're endothermic or exothermic. Now, I've given you 3 points that I want you to research. I'm not telling you whether the reaction is exothermic or endothermic. I want you to research this, looking at the chemical reactions that take place, decide whether, looking at the chemical reaction that takes place and a description of the product, decide whether it's exothermic or endothermic. So for the first one, you've got chemical hand and body warmers. So you're going to have to search about this. You're going to have to do a quick search online about chemical hand and body warmers. There's a clue here to help you with your research. I'm giving you hydrated iron oxide and sodium ethanoate. So look for those products or reactants in chemical hand and body warmers. I want you to collect information about what products have been made using these reactants or with these products, and I want you to give a brief description of how they're used and the different types of chemical hand and body warmers that are around, and do a quick comparison for that. The next one is self-heating cans. And an example of this is self-heating coffee cans. And the chemical reaction that is typically the chemical product or reactant that you may find in this is calcium hydroxide. There is more to this. There is an actual complete equation that you can get for this, but I want you to research self-heating cans or self-heating coffee. Self-heating coffee cans that have used or produce calcium hydroxide. I want you to do a quick research for this. Look at how this product was produced and how effective it was. And I want you to tell me what type of reaction, what type of reaction, was it endothermic or exothermic, that was being utilized in self-heating cans or self-heating coffee cans. The third one is cold packs. And I want you to look at instant cold packs and how they have been manufactured and how they are produced. And a clue here is to look at, in terms of the chemical reactions or the chemical products I want you to look at, is ammonium nitrate. And I want you to use ammonium nitrate as your baseline in terms of cold packs, instant cold packs. Tell me whether the use of instant cold packs is endothermic or exothermic. And I want you to give me a brief outline of how the product works and if there's any history to the product as well, how they've been made in the past. So this should take about 20 minutes. And can you put this on a separate document? And once you've finished this, so you need to research 1, 2, and 3. Tell me whether what each product is utilizing, whether it's an exothermic reaction or an endothermic reaction, and use these chemical reactants or products. I'm not going to say which one it is. You have to find that through your research. Use those words that are highlighted in blue to help you with your research. 20 minutes. When you finished it, can you upload your answers back to me on Teams?